Oh, so this is about quantum error correction. So this looks like like a rather technical, maybe slightly, less interesting topic. However, it has really fundamental importance, this idea that you can actually mitigate errors in a quantum information protocol. And so why is that so important? It's because in theory, so everything we discussed so far, quantum information protocols are based or use pure states. So really, vectors in the Hilbert space. However, in practice, there is no such thing as pure states. So pure states are an idealization. In any practical implementation, you always have some technical imperfection or some noise coming from the environment. So pure states are, strictly speaking, really a theoretical idealization. It's a very useful one. However, in practice, one should realize that you never have pure states, but you always have mixed states. You can be very close to a pure state, you can have states with a high level of purity, but you're never quite at a purity of one. So, however, in practice, noise is unavoidable. And we have only mixed states. And so the main question that appears from this is, so the first question could be, do quantum information protocols still work? The answer will be yes. And then the second question is, can we purify quantum resources? So that is, if we have resources that are not perfect. So if I have a source that creates a mixed state instead of a pure one, can I, via some process, sort of enhance the purity, or in other words, purify my quantum resource? Of course, there is another question, which is, can we control the effect of errors, for instance, in a quantum computation? And there also the answer is yes. So we are going to discuss some of these questions here and see how this can be done in practice. So the first part here, it's about entanglement purification. And that is a sort of warm-up, if you want. Now, what is the principle here? So the idea is that we have a source here that produces some entangled state. You see in a minute why this is a warm-up. So I have a source producing some state here, which will be imperfect in a way that I will make clear in a minute. And then this state here is then distributed to two parties, Alice and Bob. And so then the question we ask is, can we, via some procedure, transform this shared state here into a perfect one? So here in my example, a perfect one would be a Bell state. think, for instance, that I would like to use this pair of entangled particles to do teleportation. So then I need a Bell state. And as first example of some imperfection, I would imagine here that my source produces a state of the following form. Okay, so you see what I have here is a partially entangled state, and I would like to go to a maximally entangled state. So this is a Bell state. Okay, and indeed, I mean, teleportation is one example of a task where this would be desirable, but there are many others, right? So again, the point is that in my lab, I only have access to a source that is imperfect. I don't have access to a source that produces, perfect Bell states. And so in this example here, it is a slight idealization. This is not extremely realistic neither, because I'm already preparing a state that is pure. Okay, but it's just not maximally entangled. Right, so here I will imagine that theta is between pi/4 and 0. Okay, so I have some entanglement, but it's not maximal entanglement. And the question I ask is, can I convert this via some relevant procedure here to a Bell state, right? So can I increase the entanglement of this available state in order to get a Bell state? And then once I have the Bell state, I do whatever I want with it, like teleportation or something else. Okay, so here is the idea of how it works. So there is a remark, something that is important here, namely that our procedure for purifying entanglement, it should involve only LOCC resources. Okay, so remember, LOCC means local operation in classical communication. So these are the operations that cannot increase entanglement. Okay, and you see why I'm asking this, because of course one very silly way to go from here to there would be to say, oh, I have an imperfect source, I just throw the state in the bin and I use a perfect source that creates that state. Okay, but of course here I cheat, right? Because I assume that I have for free a resource that is already the best possible one. Okay, so I would like to do this step here, doing only LOCC. Okay, so I will manipulate my state here in a way that does not create entanglement, and I will go from a partially entangled state to maximally entangled one. Okay, now a priori this sounds even a contradiction, right? Because I said my LOCC cannot boost the entanglement, so how come I can go for something that is weakly entangled to something that is maximally entangled? The point will be that this does not work each time, right? This is a process that will work with a certain probability. However, it's a heralded process, so when it works, I know it worked, and therefore I know that A and B now share a Bell state. When that is the case, I can go on with the protocol I would like to implement. Okay. Maybe I should write it here. So the procedure will be probabilistic, so it will not work every time, but it will be heralded. So when it worked, there is a signal, or there is a way for me to know that it worked, and therefore I can go on and use my output entanglement. Okay, so here is our protocol. Maybe let's write it again. So my protocol here, it will be very simple. So I have my state psi. Let me write that this is a psi of theta here. So this is the state psi theta. And what I'm going to do is I will involve here a filtering on Alice's side. And on Bob's side, I will do nothing. Okay. So the point is this filter. What does it do? Let's see exactly what I want to do. Yes. So it is going to absorb the state 0 with some probability. Okay, let me use the same notation as in the notes, with probability 1 minus t. So the filter does these two things. It's absorbed the state 0 with some probability, and it does nothing to the state 1. Okay? So that is, if you want, it's a sort of partially polarizing filter, right? So imagine that 0 and 1 are the polarization state of a single photon. So 0 is H and 1 is V. So you see this filter here, what it's doing is that when vertically polarized light comes in, it does nothing, so it lets it through. And when horizontally polarized light comes, it absorbs a part of it, right? So there are some horizontally polarized photons that will go through and some that will be absorbed in the filter, right? So it's a partially filtering operation. And that is well defined. Of course, I can have that in the lab. For instance, via polarizer or sunglasses, as you prefer. Okay, so now here is how it goes. So initially I start with my state psi theta, which is cos theta 0, 0 sine theta 1, 1. And remember, because I work in this parameter regime, I have that cos theta is larger than sine theta. Okay, so now I filter. And so you see what the filter is doing is it's acting on the first Hilbert space here, okay? And on the 1 degree of freedom, it's doing nothing. So I will just copy it back here. Sorry, like this. And on the 0 degree of freedom, there is this filtering, right? So it means that my probability to go through is t, right? And here, because I still have a pure state, so what I write here, amplitudes of probability, I have to put the square root of t in front, right? Because the probability of transmission will be the square of this, so then I get t. That is the correct thing. But here in amplitude, I have to put square root t, and therefore you see this is the state that comes out of my polarizer. Okay, and you should note that this is an unnormalized state. And this, because this follows from the fact that part of the the light or the particles are absorbed. Right, so here I only describe the state given that something came out of the polarizer, right? So therefore, this is not normalized. Okay, and now, well, you see that from this equation, so I should choose T to be the tan squared of theta, right? So you see theta is the level of entanglement of my source. So that may not be perfect because my source is imperfect, but this theta might be known to me. So if I know theta, well, then I should choose T, the transmittivity of my filter, to be given by this relation. And therefore, well, then this final state here is what? Well, then this is just a Bell state, right? This is equal, let's put it maybe like this. This is equal to, you will have a sine of theta here times 0, 0 plus 1. Okay, and so therefore I have a Bell state. So maybe let's write it here. So I have a Bell state whenever something comes out from the filter. Okay. Of course, then I should also look at what is the probability of success. So this procedure does not always work. And in fact, I can compute the probability of success. And the probability of success, this is just the norm of this state here, right? Oh, sorry, you don't see. The probability of success is just the norm of that state. Okay, so the norm of that state is what? Well, I have to put this parameter inside, but you find it easily, or you can find it from here. The norm is simply twice the sine squared of theta. Okay, so here you see I have sine of theta, but this is, here I wrote a Bell state that is not normalized. So if I would add a root 2 here, I would have to add a root 2 there. Okay, and therefore, now that I have a normalized state here, I can compute the norm with this thing, and the square of this is indeed 2 sine squared. So this is my probability that it works. And you see that, so if theta is close to pi over 4, right? Okay, that thing works with probability that is almost 1, right? While if I have a source that is already highly entangled, though not maximally, this procedure will work relatively well, very often. But if I start from a source, on the other hand, that produces only very weak entanglement, okay, then my probability of success will be much lower. Okay. So that is a very simple procedure. As I said, it's a bit unrealistic because you see in this example, I started from a, so let me put the setup back. So here I started from a state that is already pure, though weakly entangled. However, in experiments, I will typically have a mixed state here, right? I will have some, maybe some Bell state mixed with some amount of noise. And this is what we are going to discuss in the next example, how to do something similar to this. So how to purify, how to concentrate the entanglement of this initial state into something that is more entangled, right? And then more useful for me for my future applications. maybe just a quick note here before we start. So in fact, the above procedure is in fact not optimal. Okay, so what it means optimal is that here I have a probability of success that is given by this equation, and of course this really depends on the exact purification procedure I implemented. So that procedure I just described is very simple, so it's easy to understand, but it's typically not the best I can do. So I could do something more complicated, and then I would get better. So in particular, what I could do is I could start from, so instead of handling one copy at a time, I could handle many copies. So this would be psi theta tensor n, and then I could try via some LOCC here to transform this into m. So these would be Bell states now. So this would be phi plus, and here I would have m copies. Okay. So here you see the difference is that now I process n copies of my imperfect source, of my imperfect state, and I try to make out of these n copies, m copies of a Bell state. Okay, and so in the asymptotic regime, so the asymptotic regime means that n goes to infinity. One can show that the optimal procedure here will be such that m over n is given by the von Neumann entropy of the state. Okay. So this is the so rho A here would be the so this is the partial trace over B from this state. Okay, and so therefore this is the Shannon binary entropy of the distribution cos square theta sine square theta. Okay, and here where rho A is the partial trace over B of psi theta, psi theta. Okay, so this is actually quite nice, you see, because it gives some sort of operational meaning to this quantity, right? The von Neumann entropy of the reduced state. I mean, we saw previously that this is a measure of entanglement, although we didn't quite explain what actually it measures. Now you see in this example here, well, in fact, maybe I'm a bit sloppy here. Maybe I should say that this tends to rho A. Okay. You see this von Neumann entropy for my state represents somehow the fraction of singlets I'm able, or the fraction of Bell states I'm able to extract out of n copies of my imperfect state. Okay, so you see it's quite a nice machinery somehow. All right. So now I should move to the second point, and this is now the purification of noisy entanglement. And so the point here is to make this a bit more realistic. Okay, so now the idea is that, so again, I have a source that produces now some mixed state rho distributed to AB. And this mixed state rho, I will write it like this. Okay, so phi plus and psi plus, they are two of the Bell states. Okay.
Sorry, Nicholas. Sorry
yes.
to interrupt. I think because of the light from the window, the camera adjusts the brightness such that when you remove your hand, we don't see any.
Yes. I see. I think this is because it's quite, it's not really sunny today, but it's too dark now. Is it better now?
Now it's better, thank you.
This. Is it good or was it better just before?
It's better now. I mean,
it's better now. Okay,
it's
good.
Perfect.
Good, thanks.
Thank you.
Okay, so let me go back here to this more realistic scenario. So imagine now that my source here produces a state of this form. And so if you want, this is my target state. So again, I would like to have a phi plus, right? Ideally to run my teleportation. But the state I can prepare in the lab looks more like this. So here I have a part that is good, right? And here I have a part that is bad. So this is somehow the noise, okay? So you could imagine that you see you have a source here that produces some entanglement, 0, 0, plus 1, 1. But every now and then there is a sort of flip in here. And so instead of producing phi plus, I produce psi plus. So that would be a 0, 1 plus 1, 0. Okay, so I have a sort of bit flip here. All right. I will nevertheless assume that you see my sources. It's not perfect, but it's still relatively good. And that means that f is greater than 1/2, right? If f would be smaller than 1/2, then in fact you see what I call the noise here would be more prominent. And so therefore, instead of trying to make a phi plus, it would be easier if I try to make a perfect psi plus, right? Because anyway, this component is larger. Okay, so that regime here is the one that makes sense. In fact, I didn't define what is f. So f here is the fidelity. Well, okay, in fact here, f is just a mixing parameter. So f is f and 1 minus f define a probability distribution. But you see f here, I can also understand it as the overlap. This is the overlap of my state here, rho, with the perfect state. Okay, so this is really the fidelity of rho with respect to the target state, which is phi plus. Okay. And so the goal here will be to, okay, loosely speaking, it will be to boost f. So I would like to manipulate now locally here. So again, via LOCC, I would like to manipulate this state here and obtain out of it something that has a higher fidelity, right? So something that is a bit closer to the target state. And to do that, I will here actually need 2 copies. Okay, before, when I had a source producing a pure state, it was enough that I took 1 copy and I put a polarizer. Now when I have mixed state entanglement, I generally need more than 1 copy. Okay, so I'll need to process at least 2 copies, but turns out 2 copies work here. Can already improve. So here is the scheme. Okay, I was planning to do it there, but maybe I copy it again. So I have my source here producing row. I will write here another source that also produces row, but I could just imagine that, you know, it's the same source used at different times, right? So that's a way to produce 2 copies of the same state. And so now on Alice's and Bob's side, I will have to process these states. And in fact, so I will need here very small quantum circuit. And this is how it looks like. And it's exactly the same on Bob. So if you remember, this symbol here denotes a C0 gate. And what I write here is this is a Z measurement. Okay, so this is a C0. And this is a sigma Z measurement. All right. Okay, so now this thing here, you can write it as a sort of little box. And what I claim is that if I do the right operation now, the state that comes out, okay, so the state, maybe I should do it in color. So the state between this particle and that particle, it will be more entangled than rho, okay? Turns out it will be a state of the same form, okay? So I'll show you in a minute that the final state here will be exactly of that form, but it will have a different coefficient here, which is larger than this one. So then my claim that the output state is more entangled than the initial one is really justified. All right. So here is how it works. Okay, maybe I should add something about the protocol, because there is something non-trivial. It's just, you see, because I put these circuits here and then I measure, and the point is, so this is a binary measurement, right? Which it has eigenvalues 1 and -1. 1 and -1. And so the protocol is that if both A and B obtain the same measurement result, they keep. So that means, so you see these particles, they are kept in some memory. Maybe it's an atom now that carries this information here, or if it's a photon, maybe this photon is either frozen into some material or it's kept somewhere, right? And then via LOCC you can compare, right? So Alice can tell Bob, oh, I got the result +1. Then Bob can say, okay, good, I also got the result +1, so we keep. So that is what it's meant here by they keep. And the point is, otherwise, they throw away and restart. Okay, so if you obtain different results here, okay, you throw away these 2 copies, the protocol didn't work, and you start again. Okay, so that's, again, it is probabilistic. It doesn't work every time. Okay, so now let's investigate this more formally. So we have an initial state. and our initial state is rho tensor rho. Okay, so by linearity we can write what this is. So this is f squared times, so let me use this notation now. So these are the projector on the Bell states. Okay, so maybe define it here. So p phi plus, this is equal to the projector on phi plus. Okay, and now I have, you see I have two copies. So I have twice the projector on phi plus with a coefficient f squared. So that represents, it represents the first component here of the state, right? And I take it twice, so that's why I got the f squared. And so now I develop, so by linearity I have 4 terms. So here they are somehow the cross terms, and these have the same coefficient. And I have the last term, which is 1 minus f squared. And this is p psi plus, p psi plus. Okay, so that's fine. So now to compute, it is convenient to apply C naughts on each component individually. So of course I could write a big density matrix, right? Would be 16 by 16 here. And then I could apply the unitaries for the C naught, but okay, this is a bit cumbersome. So it's much faster if I apply 2 C naughts now on this object here. By linearity, I can compute it for this term, for this term, for this term, for that term, and then I put everything together. And so if I do that, I can see the following thing. So okay, because each term now is corresponds to a pure state, maybe I just write it like this, right? So when you have phi plus, this will, you can check, it will actually go to phi plus, If I have phi plus, psi plus, this will go to phi plus, psi plus. So you see, the idea is whenever the first state here is a phi, nothing changes, okay, on the second copy, right? I mean, anyway, the state of the first copy cannot change because here I only have the controls, right? So the changes can only be on the second copy where the C naughts acts with targets. Now it turns out that when the first state is a psi plus, the control states, then I actually flip the target. So what happens, is that this thing here goes to psi plus, and this goes to psi plus, phi plus. So you see, in a sense, the only thing that happened is that I inverted these two terms, right? So these two, they got switched. Okay. Now, remember that in our protocol there is this step here where I perform now Z measurement at the output of the target qubit on each side, and then I check the parity between the results, right? So essentially, for phi plus state, the parity will be 1, therefore I keep, right? The results will be the same because the phi plus is a 0, 0 plus a 1, 1. However, if the state is a psi plus, like here, for instance, this is a 0, 1, 1, 0, and therefore the parity will be minus 1, right? So therefore I will throw away. So here is how it goes. This I keep. Okay, the last term here I keep as well, but this here this I throw away and this I throw away. Okay, so out of my 4 terms, I will actually keep only 2. All right, so maybe let me put it like this. Okay, so the final state, this is when the operation is successful. Okay, when I keep. So this is a row prime. And you see, so this is a state that has only 2 components, right? Which are these ones, this one, sorry, and this one. And remember, what I'm interested in is the state of the first copy, right? So I'm interested in the state between these 2 particles here. The second pair, I perform the measurement on it, right? So anyway, it's has been destroyed. So if I look at this, maybe I should go back here, right? So you see, I have one term that survived, which is the first one here, right? So with probability f squared, what survives is a 5 plus, 5 plus, but again, the second part I measure anyway, so this I don't write. I'm only interested in the first part. So here, with probability f squared, I get a 5 plus, and then I have this second term that I keep here. Again, the second system is in 5 plus, but this is the one I measure, so I will not write it. So the first part, which is the relevant one, this is in psi plus now. So this is a p psi plus. And you see this came from this final term here, psi plus, which has probability 1 minus f squared. Okay, so that is my state. However, notice now that this is a normalized state, right? Because f squared and 1 minus f squared do not sum to 1. So I'm going to renormalize the state. So I'm going to divide by f squared, 1 minus f squared. Okay. So here I renormalize. And note that the probability of success is just my normalization, right? This is f squared plus 1 minus f squared. Okay. So now I claim, so you see this thing is of the form, f prime p phi plus 1 minus f prime p psi plus. So it's exactly of the same form as the initial state, as I claimed. And what is important now is that, in fact, I can easily check that this thing here, this is greater than f. Okay. So I conclude that entanglement has been purified. Okay, there is another word for this, which is concentrated. Okay, so I didn't do the calculation here, namely these steps. In fact, I think it's the first exercise of today's tutorial, I propose to you to look at a generalized version of this, which in fact makes it fully realistic now, I would say, because that would be the case where you see here, I have a state that is not of maximal rank, right? So you see I have a mixture of two orthogonal components, each one being a pure state. So the rank here of this state is 2, right? However, in experiments, you see it's very, so you never have pure states, but you also never have non-full rank states. You will always have a noise that is sort of isotropic, that scans or that spans the whole Hilbert space. So what you will do in the exercise is that the noise term here consists in fact of the 3 other Bell states, okay? Not only the psi plus, but also the psi minus and the phi minus. And then you have a density matrix here that is full rank, right? And okay, you will see that the same procedure here does actually work in general. Okay, so that is really the case that is interesting in practice, where you have full rank entangled states. But the calculation is just the same. So I let you do it in the tutorials. Okay, but maybe we could discuss again what we did here. So you see, so what we did is that we started from this scenario here. Maybe I write it in blue. And then with some probability here, we managed to create now more entangled state that we called rho prime. Okay, and so that's why we also talk about entanglement concentration, because you see what we did is that we started from 2 copies of a state, and each one had small entanglement, right? Now, with our LOCC procedure here, in the end, we end up with 1 copy of a state, when the procedure works, right? And this copy now has more entanglement than the initial one. And here you see this is what we call it entanglement concentration or entanglement distillation, because we started from a resource that had weak entanglement. As an analogy, you could think of a fluid with a weak level of alcohol, and then you distill it, right? So then you reduce the quantity, but you see, you evaporate only the useless thing, right? So you evaporate the water or whatever, and so all the alcohol now gets concentrated in a smaller volume, right? And this is the same idea here, right? So you start with low entangled states, and then you concentrate or you distill their entanglement into 1 copy, so to a lower volume, but now that has a higher concentration of the resource. Okay. Any questions so far? Okay, good. So I suggest to make a small break. Maybe let me go just get a glass of water, and in 2 minutes we can discuss the exam. And in the second hour, we discuss error correction. Okay, and now I do this. Whoop. Okay, so let's continue. Where's my pen? It's this one. Okay, so now we move to the last part, which is quantum error correction per se. And you see, so this is this has essentially, so the goal here is to correct errors in, for instance, a quantum computation. So if you have a circuit, right, where you do many gates one after the other, of course it will be unavoidable that each gate has some level of error, some noise. But in a typical computer circuits, you have thousands, millions, or even tens of millions of gates, right? So if each one has a little error and all these errors sum up, quickly, your computation would be completely out of control, right? And in fact, this is an argument that some people used in the early 90s. So when Shor and all these people came up with the first quantum algorithms, presented as we did here with pure states and perfect unitary gates, then some people said, but wait a minute, in practice, you will never have pure states, you will have mixed states, there will be small errors in each gate. Cannot do a perfect C0 gate, it's not possible. It will always be a small percentage of error. And so therefore, people argued, because you have to do thousands or millions of gates to make this interesting, well then, this thing will be completely out of control, right? And I think that this reasoning you can understand intuitively, because you see, if you have so if you think of classical error correction, right, which is of course very important, this is also implemented in my computer here or in any electronic device, right? Because there also you have lots of gates. These gates are not perfect, and each one has a little probability of an error, and therefore you also have to mitigate errors and bring them under control. Now, when you have classical gates manipulating classical information, the typical thing you do is you use redundance. So instead of encoding the information once, you encode it several times. And a bit in the idea of the code words that we saw last week. And with this redundance, you make sure that you can keep track of error and eventually correct them. And if you do that step by step in your calculation, you can keep everything under control. However, you see, the idea is that typically monitoring errors implies that you use measurements to check whether there has been an error or not. So this is okay classically because measurements have no influence. However, in quantum mechanics, if you start to make measurements, well, then you may destroy the coherence of, for instance, the entanglement between your qubits in a quantum computation. And so that's why people thought that because to do error correction, you have to rely on measurements. They thought it will never be possible to do quantum error correction. However, well, fortunately, let's say, this turns out to be wrong. Okay, so you can actually do quantum error correction. And in fact, the first protocol that was discovered, I think it was also by Shor. Okay, so yeah, clever guy. So here we are going to see the simplest scheme. That is this is the 3-qubit code. So this is the simplest, what people call an error correcting code. So the idea is use redundance. And what this means is that we typically want to encode one logical qubit. So what I call a logical qubit is the one that I really use in my computation. And this logical qubit, I want to encode it onto several physical qubits. Okay, so the point is that the noise will act on the physical qubits, and if I do my encoding well, then this noise, although it affects the physical qubits, it can be corrected with respect to the logical qubit. Okay, and therefore I can keep track of the errors. Okay, so let's look at the scheme. So I have here some initial state that I call phi. This is the state of a qubit. And that state will have to go through, so I take a model here where I'm going to pass this is a qubit state here, and I will map, I will pass this state through a noisy channel, right? So this is a noisy channel. So what comes out here is a noisy version of this state, okay? So this noisy channel could be, for instance, you could think of it as a gate, right? It could be a gate that would apply unitary on this, and it has a bit of noise. It could also be just a wire in your quantum computer where the qubits just go along this wire, and then there is a bit of noise. It's actually also something you could use for communication. If this is a long distance channel with some noise and you want to communicate over it, you can also use this procedure here. Okay, so as I mentioned, the first point is that I will have some extra qubits. So it's the 3 qubit code, so there are 2 extra qubits. And these, they are going to be now correlated to the initial qubit. Okay, so here again I draw C nodes, and this is my the first part of my scheme. It's the encoding. Okay, so now you see what I do is that I take that my input state here, my input qubit state, and then I encode it into so if you want, this is my logical qubit, and then I will encode it onto these 3 qubits here, and these are my 3 physical qubits. Okay, now each of these 3 qubits should go through the noisy channel, right? If I would assume a perfect channel, let's say here for the last qubit, of course I would cheat. Then it would be very easy to cheat actually, because I could just send that wire to this channel here, right? And then I would have no noise. So of course, if I want to make it meaningful, I need to have the noise on each of my physical qubits. Okay, so then after the channel, I go through a relatively important step now. And this step involves now 2 further qubits. And now I have a circuit which goes like this. Okay. Let me draw it and then we discuss it. No, sorry. So this is wrong here. Okay, so the control is on the third qubit. Okay, so that is a big box, which I will close here. So that is the recovery box, the recovery operation. And so in the final bit, I have the decoding. All right. And so this is the decoding here. And then what I claim is that in the end, I will, well, I mean, ideally, I would like to have my output state here, right? But we will, okay, in general, we will not have it perfect, but we will see that we will have something that is much better, of much higher fidelity with respect to the input state, compared to the case where we would just send this one through a channel, right? Okay, so you see it's a bit of a, looks a bit complicated, has many steps. So this last box is the decoding here. And in fact, so this is the, maybe, okay, let's go through the circuit and explain the main idea. So again, we start with a logical qubit, first encoded in one physical qubit. Then we do this encoding where our logical qubit goes to 3 physical qubits. Then the noise acts on each one here. Then we have 2 steps, right, after the channel. First, we have a recovery, and this step here, so the goal of this one here is to estimate and correct errors. Okay, this is the goal of the recovery. So what we do here is we add two further qubits, and so out of these things so when we look at the result of these measurements here, so this gives us what is called the error syndrome. Okay, so this is our, if you want, the estimate of our errors. And based on this, maybe this we could draw in green. Based on this, we are going to apply some changes to our 3 physical qubits. Okay, so this denotes some sort of feed forward here, some operation that I will apply on these 3 qubits depending on what my error syndrome is. Okay, and once I did that, then I have still my 3 physical qubits that are now error corrected. And okay, you see the final stage is the decoding, which is the same as the encoding. And if I wanted to get my 3 physical qubits back to a single logical qubit, I would do it this way, okay? All right. So now let's go to the math. It's a little bit tedious, but it's not too bad. So here is the idea. So first we have our initial state. In our initial state phi, this is going to be a superposition of 0 and 1. It's a general qubit state. Then I have the second step, which is the encoding. Now in the encoding, what happens is that I take phi, and then now I take 2 ancilla qubits, each one prepared in the state 0, and then via this circuit, okay, so this is the encoding circuit. Well, you see in fact what happens. So I have, you see by linearity, I have a first term which coefficient A, and then I have a 0. So when this is a 0 into the control of these C nodes, well, these C nodes do nothing. So I have my 3 qubits are in the state 0. And then I have a second term where my first qubit is in the state 1. So then the control of these 2 C nodes is 1. So I flip these 2. And therefore I have a 1, 1, 1. Okay? So notice that this thing here, so this is an entangled state in general. Okay? But you see the idea, right? This is very natural. So I had a single qubit state, so my logical information are the coefficients A and B, if you want. And now somehow I map these to a 3 qubit state, and you see that I have some sort of redundancy here in the way the qubits are encoded. Okay, so then comes the channel. Okay, so now there is some noise in the channel, and so here I will go through a list of all possibilities. So I will write the output state and the probability. Okay, the input state is always this one. Okay. So of course it can be that the output state is equal to the input state. Okay, and that happens with probability. Okay, I didn't define the noise yet. Maybe I can do it here. So the noise is in fact a bit flip. So the noise is a sigma x. And this happens with probability P. Okay. Okay, so here you see there was no noise on either of my physical qubits. So this has probability 1 minus P cube. Okay, this is the probability that there was no noise on either of these uses of the channel. So then I have those cases with a single error. So if I would apply, for instance, a bit flip to the first qubit, I get this, right? And this has probability P times 1 minus P squared, right? There was one instance of noise, if you want. And here, in fact, there are 3 possibilities by symmetry, which are these 3. Okay, that can be, so all these terms have the same probability because this is when there is only one instance of a bit flip, and it can be in the first, second, or third qubit. So now come those cases where there are 2 errors. Okay, I can rewrite everything. Just out of completeness. Okay, and so these have probability now P squared 1 minus P, right? There are two instances of a bit flip. And finally, I have the one that is really the most dramatic case, where there is an error on every physical qubit. And this has probability P cube. Okay. So I'm typically interested here in the regime where P is smaller than 1/2, right? I have noise, but it's not so bad. And therefore, you see, so somehow this is very unlikely here, but it can happen. This is in a sense, the most likely case. And then there are the cases where I have 1 error, and a bit less likely other cases where I have 2 errors. Okay. Good, so I move to the fourth step, which is the recovery. And that is performed by Bob now. So in the recovery, Bob adds 2 extra qubits, and these are in the state 0, 0. Okay, so these are represented here. Okay, and now I go on with the computation, and now he applies all these C0 operations. Okay, maybe, well, okay, maybe I do it again, otherwise it would be confusing. So I have the output state, the probability, and okay, maybe I write it here. This is the syndrome. Okay, so the first case, I had the output state 0, 0, 0 plus B 1, 1, 1. Okay, now you see what's going on is that I should show you the circuit again. Actually, maybe I will do it here because then it allows me to still show you the circuit, which will be more useful, I think. Okay, so now maybe I do it in blue. So in blue here, I will write what is the syndrome. Oh, maybe I do it here. So this is the syndrome for Bob. Okay. So what I'm interested in is the state of these 2 qubits here as at the end of the circuit. So this is where I will measure, right? And here I will measure in the Z basis each one. Okay, so the first thing to notice is that the output state here of these 3 physical qubits, this is the same as the state here, right? This is because all these C0s, they have their controls here. Okay, there is no target on these first 3 lines. So the state here is the same as there. What changes is the state of the syndrome qubits. Okay, so now you see what is measured here tells me something about the parity between these 2 qubits here, right? Between the first 2 physical qubits. Because if I have a 0, 0, for instance, right? Okay, then these C0s do nothing, right? So then this qubit here is in the state 0, and it will be measured as such in the end here. If these 2 qubits are 1, then you see each of the C0s induces a bit flip. So I have a sigma x here and a sigma x there. But because sigma x squared is identity, again, I will have the identity in the end. Okay. Now, if I have different parity between these 2, if I have a 0 here and a 1 here, then I will have no flip from here and a flip here. Okay, and therefore I will measure a 1, right? And the opposite, so if I have a flip here and not here, will also give me a 1. Okay, so by measuring the output state here, I know the parity between these 2 physical qubits. I don't know what they are. I don't know if they are 0, 0 or 1, 1, but I know that they have the same parity or not. Is that clear?
Yes.
Okay, wonderful. So let's look at what happens here, right? So here is my case where I have no error. Now you see, so there are 2 components of the state, and remember that it's the first 2 qubits here that act as controls, right? Now you see these first two qubits, they are either 0, 0 or 1, 1, so they have the same parity, right? So in any case, the syndrome, the first syndrome qubit will be in the state 0. And you see what the second syndrome qubit is. Well, it's exactly the same. It's now just a measurement of the parity between the first and the third qubit. Okay, you see it's exactly the same circuit with the difference that here the control is on line 2 and here the control is on line 3. So this syndrome qubit tells me what is the parity between physical qubit 1 and physical qubit 3. And again, if I look at that state, you see immediately that the parity is 1, so the state is 0. Okay, now let's move to this second case here. So here the parity between the first two is not 1, right? The parity is -1, they have different parity. So here my syndrome qubit will be a 1. And if I compare now qubit 1 and 3, this is also 1, okay? Now let me move to this case. Here again, the parity between 1 and physical qubits 1 and 2 is different, okay? So I have parity -1, I have a syndrome qubit in the state 1. However, between qubit 1 and 3, they have the same parity, right? Actually, sorry, here I did it wrong. So this is a 1, 0, 1. Yes, sorry for that. Okay, but you see, so I hope it's clear. No, the first two qubits, they have different parity. The first and last, they have the same parity. So then the state I have here is 1, 0. And for the last one, well, here I have same parity for 1 and 2. So I have a 0 and I have a 1. Okay, and I can continue this thing here. So let's see, this is going to be 0, 1. This is going to be 1, 0. This is going to be 1, 1. And this is going to be 0, 0. Okay, good. Okay, so now here is the important thing, right? So you see, in the end of this recovery channel, I measure these two qubits, right? This gives me my error syndrome. So I can measure these two qubits in the logical basis. So I know if it's a 0, 0, a 1, 1, a 0, 1, or a 1, 0, right? So I can differentiate between these four cases. However, if I get a 0, 0, you see there are two possibilities. There are these two. So if I see a syndrome of 0, 0, I know that either there was no error or there were 3 errors, right? Similarly, if I see a 1, 1, I know that either there was 1 error and this error was in qubit 1, or there were 2 errors here and these errors were on qubit 2 and 3. Okay, and it's the same for the last two, right? So this is the remark. So by measuring the error syndrome qubit, I learned something on how many and where the errors happened. Okay, so importantly, I don't know for sure what happened, right? This I cannot do. But I know something, right? So remember, if I see a syndrome of 0, 0, I know it was one of these two. Now, why is that useful? Well, this is useful because you see there is noise but there is not an overwhelming amount of noise, right? So the probability to have a bit flip is smaller than 1/2. So if I know it's between these two cases here, well, then I know that this is much more likely than this, right? So therefore, I will base my, my correcting procedure here, represented by these green arrows. I will base that procedure on the most likely case, right? So namely, if I measure a syndrome of 0, 0, then I will do nothing, right? Because it's much more likely I got the correct state already. Of course, there are cases where I will get it wrong, where it will be the case that there were 3 errors, and this will induce an error. But the point is that this will be very unlikely, and therefore, on average, I'm going to win. Now let's do another case. If I see the syndrome to be 1, 1, I need to compare these two. So it could either have been that there was 1 error in the first qubit, or 2 errors in the second and last qubits. Again, this thing is much more likely than this. And therefore, what I should do is that I should correct the error in this first qubit. Again, I cannot prevent bad cases where it will be this here, where there have been 2 errors, and then my thing will introduce an error. But again, because this is more likely than this, I'm going to win on average. Okay, that's the idea. Okay. So maybe now, like it's so maybe I should forget about this. So now what I need to tell you is for each syndrome, what is the correction? So there are 4 possibilities. So if I have a 0, 0, this is the case that we discussed before, I do nothing. If I had a 1, 1, I do a sigma x on qubit 1. And you see if I have a 1, 0, I do a sigma x on qubit 2. And if I have a 0, 1, I do a sigma x on qubit 3. Okay, that's the... So again, this correction procedure, this is tailored to the most likely case in this table, right? Maybe I should write this. So this is tailored to most likely case. All right, okay. Almost at the end here. So do I? Yes, okay, maybe I can just discuss quickly the decoding. You see the decoding, if I go back to here, this is exactly analogous to the encoding, right? It's exactly the same circuit. Note that these two C nodes, they commute, right? So if I do them like this or the other way around, it's the same. And you see that has just what this does is just to map back these 3 physical qubits to my unique logical qubit here. So maybe, I guess this I don't need to discuss too much. So this is analogous to encoding. Okay, so what I want is out of 3 physical qubits, I want to get a single logical / physical qubit. Okay, I mean the logical qubit is anyway the same in both. No, it's carried here and then mapped back to there. Okay, so now that we are in the end, we have to discuss the performance. Okay, so I have to average things out and see if I did actually win on average. So what I need to calculate is the probability to have an error, and that is on the output here, right? So after, so I'm interested in the probability of having an error at the end here, right? Now, when do I get it? So when do I get it wrong, right? So in fact, if I go back to this table now, you see for each result of the measurement syndrome, the error syndrome, there are always two cases. One is good, one is wrong, right? You see, let's do it for the 0, 0 case, okay, these two. If I apply my decoding to that state, okay, I get again the initial state, A0 plus B1. If I apply the decoding to that state, I get a A1 plus B0. Okay, so in that case, there would be an error. Now, and it's exactly the same everywhere. And so the point is that the error probability is P cube plus 3 times P squared 1 minus P. Okay, so if you go back to this table, remember, in a sense, if I draw a line here, I separate the good cases. You see, these are the good cases because in here I will correct error. So here I will get phi in the end, okay, because I correct the error. And these are the bad cases because here I will get a bit flip, so I will get a sigma x of phi. So here I have an error. Okay, and so now I just need to calculate the probability of this error. So it's 3 times this probability here plus P cube. Okay, so now that thing you can develop, and you can immediately see that this thing is smaller than P. Okay, so the point is, without error correction, the P error is P, right? Because I send my qubit through the channel, and with probability P, I have a bit flip, an error. And if I do with error correction, okay, maybe I should put this in brackets. So with error correction, my probability of an error is this expression, which is strictly smaller than P, okay? So it's good. So we corrected at least some errors, okay? I mean, the error rate is still non-zero, right? In fact, there will always be errors. But the point is, you see, I could even think of bootstrapping this procedure, and then I can really bring down the error rate to something arbitrarily low. So we have corrected errors. Okay. So maybe the last thing that we can just quickly say here is that we can quantify the improvement. So the improvement is by a factor. Well, okay, you see this expression here. The leading term here is a 3p squared, right? There is another term in p cubed, but that is much smaller. So essentially, the improvement factor is 1 over 3p. Okay, this is by how much we manage to reduce the errors. And so if, just to have an idea, right? So this improvement factor is more or less 30 for p equal 10 to the minus 2, so 1% error, and it would already be 300 if you have a smaller error, right? So if your error is 0.1%. So this, this shows that you see this procedure is, you see 1% error is something quite reasonable. At least the percent range is reasonable. And so here already a factor 30 improvement is very nice. Okay, so maybe, so are there some questions on this? So the derivation is a little bit tedious, but okay, I hope you could still follow. Maybe just a couple of little comments here. So I guess one thing you could wonder, no, is that in this scheme here, what we do is we compare the parity of the first two and qubits and the parity of the first and third qubit, right? So by symmetry, you could think, maybe we should compare the parity of the second and third. But okay, that is useless, no? Because if you have 3 qubits and you know the parity between 2 pairs, the parity between the last is already fixed, so you would not gain any information by doing that. Now, the second remark, which is a bit less trivial, is that, you see, here we have looked at channels that are bit flips. So this is it's a specific type of error, right? In general, you could also have channels that do a phase flip. So instead of a sigma x here, it would be like a sigma z, okay? Now, you see whether, I guess you can convince yourself that whether you put a sigma x or sigma z here, it's more or less the same. You can just rotate everything, for instance, via Hadamard's, right, which exchange the x and z bases. But now, a more realistic channel would be one that has both x and z noises, right? And the point is, for these more realistic channels, you can in fact use the same idea, except that you need to add 2 more qubits. So this would now be a 5-qubit code. But with this 5-qubit code and very similar things here, you can actually correct for both sigma x and sigma z errors. So both bit and phase flips. Okay, and this is where it becomes really then useful, right? Because then you have an arbitrary type of error in your channel, and with this 5-qubit code, you can correct it. So here we just did the 3-qubit code because you see the principle, right? The 5-qubit is just the same principle, but sort of bootstrapped twice, one into the other. So it's just a bit more complex, but it's really the same idea. Yeah, good. Yeah, maybe the last thing I can say is that so these ideas, they are in fact very important. And well, as you know, maybe there is a big research effort now towards building a quantum computer. And of course, error correction there is really fundamental. So when trying to build a quantum computer, people from the beginning on, they are looking for a physical system or an architecture that is able to implement this error correction procedure. Because if you don't have that, if you have an architecture where error correction is tedious or difficult to do, then you will never be able to make it work, right? And so the point is that there is in fact nowadays a lot of research, especially in the US, on error correction, and that has been already for more than 10 years. So really building such codes, of course more sophisticated than these ones, and find physical architectures that enable efficient error correction, this is something extremely important. So far I think the most robust error correcting codes, they allow for, okay, let's say few percent errors, okay, per gate. So that is good because it means that you can imagine having a realistic gate that if it has 1% noise, means it's a very high fidelity gate, but could still be realized in practice. So with these gates, then you can do your quantum computation in an error-corrected manner. That means you can really keep track of the errors in correcting them along the circuit. However, this also requires, I mean, few percent is very little. And so it means you have to work hard in the lab to really achieve this high fidelity. And so that's why now there are, very big companies like Google and Microsoft that make a sort of race in order to build such a device, right? So each one has a different physical setup, a different technology, and they try to, make extremely high fidelity gates and implement this error correction in order to have really a quantum computer that can be used to solve problems. All right. So I guess I'll stop here. If there are some more questions, I'm happy to answer. No technical questions. Okay, then I stop the screen sharing. I stop the recording.